So today we're going to be talking about finding all the zeros of polynomial functions. We're going to start with finding zeros by hand. So we're going to talk about the rational zeros theorem. We're going to use some synthetic division. We're also going to talk about the upper and lower bound tests using synthetic division. Then we're going to talk briefly about Descartes' rule of signs, which is going to help us talk about irrational zeros. Though mostly at this point what I'm going to say about them is that you're better off trusting your calculator if you have it available. We have a couple other options. And then we're going to move into complex zeros. I'll be expecting that you're using your calculator, but we're going to talk about how complex zeros interact with the other zeros, especially in terms of the fundamental theorem of algebra. So as far as finding zeros by hand, the rational zeros theorem, which you can find written formally in your book, basically tells us how to find the nice zeros. Rational there meaning it's a fraction of integers, so not the square root ones. But the rational zeros theorem, in a nutshell, says if a polynomial has rational zeros, if it has nice zeros, then they're going to be fractions such that the top of the fraction is a factor of the constant term at the end of your polynomial, and the bottom is a factor of the leading coefficient, the number in front of your polynomial. So in this case, all of our rational zeros, or all of the potential rational zeros, are going to be made out of a factor of 4 divided by a factor of 1. Because the leading coefficient is 1, that produces actually all integers. So factors of 4 are 1 and 2 and 4, and the factors of 1 are just 1. Now any of these could be positive or negative. So if we do 1 divided by 1, we get plus or minus 1. If we do 2 divided by 1, we get plus or minus 2. And when we do 4 divided by 1, we get plus or minus 4, which gives us 6 potential rational zeros. If there are rational zeros, they're on this list. So one of the things we do, if we don't have a calculator, is we check against this list to try to figure out which, if any of these, are rational zeros. As we discussed when we did polynomial division, one of the ways to check to see if something is a zero is to trust the remainder theorem, which says if we divide and get a remainder of 0, I should say, in this case, we're dividing by x minus 1, because 1 is the first 0 we're going to check. So k, in this case, is 1. We're going to do synthetic division. So we put our coefficients in for our synthetic division. If we get a remainder of 0 when we're done, then we know that 1 is a 0 of our polynomial. And if we get a remainder other than 0, it's not. So this is a quick way to check to see whether that's a 0 of the given polynomial. This one is. We found one of the rational zeros works. You could continue to check the others against the original polynomial's coefficient, but once you've found that x minus 1 is a factor, you've partially factored already. X minus 1 is a factor. The other factor is x squared minus 2x minus 4. So there's really no reason to keep using these 4 numbers when you could just use these 3 numbers. At this point also, since this is quadratic, you can find the remaining 2 zeros using the quadratic formula if you prefer doing that to using synthetic division. We would need to do synthetic division 5 more times. So actually, I recommend trying to factor using the quadratic formula. If you start with the discriminant, you will learn very quickly whether or not the answers will be rational. So let's see, opposite of b is plus or minus the square root of b squared, which in this case is 4, minus 4 times a times c, which gives us 4 plus 16, which is 20. So since this square root isn't going to work out, there's no way the other 2 zeros are rational. The other 2 zeros are irrational. That is the 2 that relate to this factor. So we actually call this, this factor here is quadratic, but we can call it an irreducible quadratic. although you should be careful about the scope you're talking about. This one is irreducible over the rational numbers. You need square roots in order to reduce this one. Let me actually finish this out then. So let's see, opposite of b was 2, plus or minus b squared minus 4ac all over 2a, which is just 2. So we've got 2 plus or minus 20 is 4 times 5, so the square root of 4 is 2. So this is 1 plus or minus the square root of 5. That's the last two zeros, 1 plus the square root of 5 and 1 minus the square root of 5. So I can, if I'm dealing with only rational numbers, this is irreducible over the rational numbers. But if I allow for irrational numbers, I can factor this as x minus 1 plus the square root of 5 and x minus 1 minus the square root of 5. Now, given that it's just algebra, I'm going to leave it to your exercises to figure out if you can multiply that together to get back to the original. But you can, and it would totally work. As far as my second example, since the first one had a leading coefficient of 1, we ended up with no fractions on our list. And I want you to see this working with a leading coefficient that's not just 1. So in this case, if we're looking for rational zeros for the polynomial 2x cubed minus 5x squared minus 28x plus 15, the top will be factor of 15, and the bottom will have factors of 2. So 1, 3, 5, and 15 on top, and 1 and 2 on the bottom. I tend to approach this systematically, so I'm going to start with 1 on the bottom, and 1 over 1 is 1. Then 3 over 1. Don't forget to make each of these plus or minus. Then I'm going to go back through and get all the 2's. So plus or minus 1/2, plus or minus 3 halves, plus or minus 5 halves, and plus or minus 15 halves. Sometimes you'll get a fraction in here that will reduce to one you've already written, in which case you wouldn't need to write it again. But since 15 and 2 are mutually prime, there's no reducing to be done here. This is a lot more zeros than we had in our last example, so it would take a long time to actually check all of these zeros. If I'm not using a calculator at all, my general approach is to start with the whole numbers because the math is much easier. And each one you find reduces the complexity of the problem because, again, you can use the other factor. Once you find one that works, you can use the other factor in your next synthetic division. This one's actually only cubic, so if I find one of these that works, then I can use the quadratic formula to find the remaining ones. So 2, -5, -28, 15. And again, I like systematic approaches. So usually I start with 1 and I work my way up looking for an upper bound. When you're using synthetic division to try to find zeros, let's see, -3, -31, well, that's definitely not going to be 0. When you're looking for the synthetic division to find zeros, anytime you're using a positive k, you may produce an upper bound. Now what that would mean is if 1 were an upper bound, then there would be no zeros bigger than 1. But in order for the test to show that 1 is an upper bound, the whole bottom row of your synthetic division has to be positive if 1 is a positive number. So in this case, because I have negatives, I haven't found the biggest one yet. Next on my list is 3, so I'll try it next. Now I didn't get a remainder of 0, so I am stuck with my original polynomial. I haven't reduced it at all yet. So bring down my 2, that's 6, 1. Times 3, -25, -75, so also not 0, -50. Then I'll try 5, 2, -5, -28, 15. So that's 2, 10, 5, 25, -3, -15, that's 0. So here I have found my first 0, 5, which means I've also found my first factor. I don't always write this. I don't usually write this, but I'm writing it in this case to make sure you realize. So I found this factor, x minus 5, because 5 is the first zero that worked. I also found the factor that goes with it. This one's quadratic. I don't know yet if it's irreducible, and I could use quadratic formula at this point. But because I want you to see the upper bound, I'm going to keep going. Now that I found this one also, dividend, the quotient here, the other factor, the number on the end is no longer 15. Now it's negative 3, which tells me in itself that the next zero is not going to be 15, even though that's on my list, because it's not going to work. Now I already tried positive 3. So when I'm looking at this polynomial, I'm left with 1 and 3 and 3 halves and 1 half. Those are my remaining options to find a rational zero. But again, the remaining zeros could be irrational. But because I no longer have zeros bigger than 5 that are possible here, I shouldn't keep going with my positive numbers. I could do a couple of the smaller positive fractions, although typically at this point I'll switch to the negative numbers. I did want to show you an upper bound, so I'm actually going to do this with 6, even though there's no way it's going to work out, because 6 isn't on my list of potential rational zeros. It will produce upper bound. It is an upper bound, so I want to show you what that looks like. If I bring down this 2, that makes 12, which is 7. Now 6 times 7 is 42, which makes this 14. Yes. 6 times 14 is 60 plus 24 is 84. So this is going to be 99. And what you'll see as you look along the bottom here is these are all positive. Now all that tells me is that there are no zeros bigger than 6, which I already knew. But if I got this result and there were still several zeros left to check, I would know to stop going bigger. Because when k is positive and all the bottom numbers are positive, that means this is an upper bound. Any number you try this that's bigger than 6 will also have all positives on the bottom. So it will also be an upper bound. Although you'll notice 5 didn't actually trigger that in this particular test. So now I'm going to switch to negatives. I usually switch to negative whole numbers. So the only ones left on my list are 1 and 3 that are integers. Integers, so negative 1. Although, again, 1 half and 3 halves are also possible. Not to mention, I haven't tried positive 1 half or positive 3 halves yet, so I need to look out for those as well. If I were actually doing this not instructively, I would have used the quadratic formula by now. All right, so I'm going to use this smaller polynomial because it simplifies the synthetic division. So when I try negative 1, I'm going to be looking for lower bound. Now for a lower bound, you need a negative k rather than the positive ones for the upper bound. And what you're looking for instead of all positive is an alternating sign pattern. So this is 2, this gives me negative 2, this is 3. So because these are both positive, they didn't change signs, this is not a lower bound. Negative 3, negative 6, nor is it a 0. Next on my list was negative 3. Again, because I'm skipping the fractions. So I bring down the 2, multiply by negative 3, I get negative 6, which makes this negative 1. Then positive 4. I'm sorry, positive 3. 3 times negative 1 is positive 3. So that's a 0. Also, you'll note this one is positive and this one is negative. When you're doing an upper and lower bound test, you can count zeros as either positive or negative, whichever suits you. They're like a wild. So I can consider that 0 to work as a positive to complete my pattern, which is an alternating sign pattern. So this proves that 3 is a lower bound for zeros. There are no zeros that are lower than negative 3. Like even irrational ones won't be down there. This leaves me with just 2 and negative 1, which looking at the rational zeros theorem, since I already tried positive and negative 1, the only options left for me are positive 1 half and negative 1 half, which I could do with synthetic division, but I'm not going to bother because this is my linear factor that's left, and it's super easy to solve even by pre-algebra students. So positive 1/2 is the remaining 0, which means my factors, if I were trying to factor this, I'd have x minus 5. That's the first one I found. Negative 3 works, so that's x plus 3. Remember, the factors are opposite. And lastly, 2x minus 1, or if you're looking for the zeros, they're 5 and negative 3 and positive 1/2. So that was sort of a look at zeros. Remember the upper and lower bound tests, which you can also look up if you don't remember. But the upper bound, you're looking at a positive k and positives all along the bottom. And the lower bound, a negative k and an alternating sign pattern to be a lower bound. Now I said we were going to do Descartes' rule of signs. I'll be honest with you from the beginning. Descartes' rule of signs is not my favorite. With the ease of use for a graphing calculator, I can't see any reason why you would want to use Descartes' rule of signs in the modern world unless somebody forces you to try without a calculator. That being said, Descartes' rule of signs is an existence theorem. It says you can figure out whether or not you can be sure to find a zero of a particular type. So coming across here, Descartes' rule of signs, you look at the coefficients and their sign. So the front here is 1, that's a positive 1. And then this is negative 3, negative 5, positive 2, and positive 7. So Descartes' rule of signs involves counting how many times the sign switches as you move from left to right. So here as we go from positive to negative, that's a sign change. This one stays negative, not a sign change. As we move over here, switches back to positives, and it stays positives. This is 2 sign changes. Descartes' rule of signs says if there's 2 sign changes, you have at most 2 real zeros. 2 real positive zeros. Now it doesn't guarantee that they're rational, but it does guarantee that they're real. Although the rule actually says you can have at most 2, it can be less than that, but it has to be less than that by an even number. So it can't be 1 real positive zero. It's got to be either 2 real positive zeros or no real positive zeros, which is the real problem here with Descartes' rule of signs, because I don't know for sure that there's 2. There could also be 0.